Hi, my name is Indranil Sanyal and I am currently pursuing Masters in Electrical and Computer Engineering. I am about to upload this video because of my curriculum in image processing and computer vision subject, which is undertaken and instructed by Dr. Oliver Wood Epang from Electrical and Computer Engineering Department, University of Florida. I would like to first thank Dr. Oliver DePang for presenting us this opportunity of conducting a project on any topic based on us. Basically, my topic today is the feature extraction using wavelet transform. We have heard about feature extraction, what it means, wavelet transform, yeah, because it's a, many of you might not have heard about it because it's a new concept. Basically, it has like around 20-25 years back it was there. It have been introduced right now. So the work basically in this domain aspect is currently going miles forward because we have achieved quite a few desirable results using the wavelet transform. So first of all, I would like to carry on what is a feature extraction. The feature extraction basically means it can be done, it can be interpreted in two ways. The first way is it is used for a dimensionality reduction. Now dimensionality reduction means what? Suppose you have an image and you only want specific features of that image. You don't require the exact image or the exact output of the image, such that because you want only the specific features, such that you can conduct your report or you can conduct your experiment based on that. So for that we use feature extraction. Feature extraction is developing just extracting the feature, meaningful feature, such that we don't require the exact image, we don't require the exact complete image, and we can do all our work with using the small parts of an image. This is one interpretation. Second interpretation, what I will tell you, if you have an image, if you have multiple images, and if you have an image which for us which is required, like we have to work under various complex variables in image processing, in science, in signal processing and everything, we have to work under various complex variables. So complex variables, what it does is it increases the memory, it increases the computation, it increases the hardware, it increases the cost. So if we want to reduce the number of variables such that it reduce the complexity, we use feature extraction feature in an image, such that we can get the image, we can work on that image with the desirable features also, not requiring necessarily not requiring the complete image. So now what I will tell you about basic feature extraction softwares. Feature extractions, in I told you about the definition. Now I will carry on what are the applications of basically feature extraction. Feature extraction is general terms or methods of constructing combination of variables, such that combination of variables to get around these problems while still describing the data with sufficiency around. Applications of feature extraction, it depends. Applications of feature extraction ranges from image motion, edge detection, corner detection, globe detection, ridge detection, scale invariant detection. Then in image motion you have basically the motion detection, which can be either in the area based or differential approach. In the shape based, you can also use thresholding, blob extraction, template matching, Hawk transform, which is a type of transforms used in the feature extraction methods, and the flexible method, which will come around active contours. Feature extraction, in software we have various softwares which are available with the feature extraction, like the wavelet toolbox, like MATLAB, Skylab, NumPy, R language. Whereas in MATLAB you have a specific feature, specific toolbox for the wavelet transform, where you can use any type of, where you can use the signal extension, image extension and everything. I will explain it to you in the later parts of the presentation. Existing approaches. Now the why, there is every time there is we require new method. Why? First of all, if an old method does not work for a particular thing, or if an old method does not give us a satisfactory result when it comes to when it comes to we want the desired result but we don't get it, so that's why we design new methods for that. Wavelet transform is such that wavelet transform is inception is has this inception from various other features only. Why? Because the Fourier transform which you used earlier did not provide us with the specific features. Now what is now you will ask me what is the Fourier transform and everything. Fourier transform was specifically designed by French mathematician Joseph Fourier, who used all these features in the Fourier transform such that it converted into time domain into frequency domain signals, and also which give us the insight into frequency components, spectral analysis. It is a very important transform, Fourier transform, in signal processing. We use in signal processing algorithms. It is always used. Then it is one of the mainstays in the Fourier transform in the feature extraction also. What it did was, it did on the what the Fourier transform did, as it works in a frequency domain approach. So what it does, it works on the specific frequencies. So if you use an image, and if you get the specific on the specific features based on the specific frequencies, you won't get the complete image, or the complete you won't get, sorry, no complete image because we don't require that. You won't get those specific image specific features which you desire. So that's why we incepted and we came through the wavelet transform. Wavelet transform, actually what it does, it's simple like the Fourier transform only. As the Fourier transform detects or breaks down the signal into a bunch of frequencies, the wavelet breaks down the signal into a waves which are of small frequencies and limited duration. Okay, so what does the wavelet does? The wavelet has a very big advantage. What it does, it gives you the output is what, for every wave is what, for every signal is what, it is a musical note of the wave, musical note of the image. So what it does, it not only gives you a complete output of that, but it also gives you the frequency output where, and frequency note of each and every image, each and every pixel. Plus it also gives you what is required is which frequency frequency transform is used at what frequency and at why it is used, that why it is used, such that that's why the wavelet transform is used. Now I will explain you what is a wavelet transform. uh, Now there are various drawbacks also in the Fourier transform. I will explain that. Like Fourier transform distributes signal into frequency transform components. So only selected frequency components are displayed. Like I said, there is a loss of temporal process and information because on the transform by doing the transform from one base to another. They are basically based on sinusoids and cosine waves, through which we won't get all the details as compared to the wavelet, and the Fourier transform compromises on image quality and background. These are the disadvantages of the Fourier transform. Now we will see how a wavelet is designed, how a wavelet transform overcomes all this. So the wavelet transform, let me explain. Wavelet transform was designed, or it was introduced, the concept was introduced in the early 1990s, specifically in 1987, when Mallet introduced this theory into a multi-resolution theory. Multi-resolution theory is always comes into a picture of this things. A multi-resolution theory always comes in the signal processing algorithms, such that it has many resolutions. So if one object escapes one resolution, it will thoroughly be depicted in the another resolution of the object. So here the wavelets are used. It is basically designed in the 1990s by this thing. Now the wavelet idea is simple. It is, the signal is distributed into a bunch of small waves of varying frequency and limited derivation, like I already told you ahead. These provides them the equivalent of a musical image, revealing only what notes to play, but also when to play them. Okay. Now, wavelet also were introduced with the various signal processing algorithms which used. It was subband coding, quadrature mirror filtering, and pyramidal image processing. Continuous wavelet transform. There are the types of wavelet transform which are used are continuous wavelet transform, discrete variable wavelet transform, fast wavelet transform, which is basically corresponds to fast wavelet packets. Continuous wavelet transform. The continuous wavelet transform transforms a continuous function into a highly redundant function of two continuous variable translation and scale. The resulting transform is easy to interpret and valuable for time frequency. What it does, it transforms a continuous function into a highly redundant of two continuous variables. Discrete variable transform, as the name suggests, if the function to be expanded, if it is discrete, the resultant coefficients which are resulted is a discrete variable transform. Whereas in fast variable transform it decomposes the function into a sum of scaling and wavelet function whose bandwidths are algorithmically related. What it does is, so the low frequency component content is represented using the functions using narrow bandwidth, while the narrow frequency component are depicted using the wider bandwidths. Now let us go through another thing. So how I will perform the feature extraction algorithm using the wavelet transform. My first process is reading the input image. The second process is doing the pre-processing, like removing all the dust, removing all the things like disturbances and sharpen. And third is the feature extraction. Now reading the input image. Reading the input image in MATLAB is not at all that much difficult. We have to just specify the raw path in the MATLAB program where images are stored and names of each images. Afterwards, what we have to do, we have to name the images in our convenience and display them in MATLAB, such that what happens, you have to run a camera frame and a start and end frame so that you can name the files according to your preferences, and you can get the wavelet transform according to that. You can get your output image according to that. Now the pre-processing image is what pre-processing is done to avoid any disturbance or de-blurring in images. If you want to perform and if you want to get a desired result, the input must also be perfect or near to perfect. Images are smooth, then only we can get a better result. The pre-processing is done to remove all the blurriness, makes the image more smooth, sharpen the image, features should be more distinct. This is done either by a Gaussian filter, the median filter, low pass filter, Laplacian filter. In this process, I'm going to use a Gaussian filter. In the future approaches, we can use the wavelet filter because it also designs using the wavelet transform only. So the first step of the algorithm is to use a Gaussian filter was used in pre-processing to eliminate the noise in the image to improve the feature extraction. Without the Gaussian filter, the final results were approximately 33.1 for the what it goes. It uses the power to signal noise ratio. Okay, so if without the using the Gaussian filter, what we have a 33.1 PSNR. But with the help of using the Gaussian filter, we have a PSNR of power to signal noise ratio is 36.7. The reason why there is a significant improvement is the result is because the Gaussian wavelet filter smooths out some of the noise in the images, therefore allowing the feature extra selection to select better points in both the sensed and the reference image. Feature extraction. After the the images are sensed having been processed, then the images are decomposed by Dovizio's one wavelet. Why we use Dovizio's wavelet? There are various types of wavelength. Dovizio's wavelet, Haar wavelet, and everything. We use Dovizio's wavelength, which is equivalent to a Haar wavelet. The reason for using Dovizio's wavelength is because it will usually result in signal converging faster to the original signal, which means the first few signals of the level detail coefficients are negligible. So the approximate coefficients of the first few levels are very similar to the original image. DOBG multi-resolution phenomena also uses the same thing. Produces a smoother signal than DOB1 because DOB wavelets have overlapping conditions. Therefore, these wavelets are able to detect the high frequency changes in the high frequency components. Why we don't use the Haar wavelet? Whereas the Haar wavelet calculates the average and the difference of a pair of values, then slides over to 2 time unit and repeats the calculation until the end of the signal is reached. But if you use higher Dirichlet's wavelet, which are not always the solution, because a higher wavelet will cause to have a longer support, which means the detail coefficients are going to contain a significant amount of energy. Since the detail coefficients contain a significant, these will require more values to be used, so the data will not be used to complain as much as possible. Now here I have few equations which I will submit in the presentation so you can see that. After wavelet decomposition, what we do is we decomposition of both the images. The algorithm extracts the approximate coefficient from the wavelet. Now the purpose for decomposing the images to accelerate the computation speed by making the original images smaller. Once the algorithm is approximate, then has the approximate coefficients. What it does is it calculates the gradient in both the x and y directions in the input and the base image, and only the maximum gradient in each row is saved. because that is where the edge point should lie, since it is an area of the grid testing where we have to detect the edge points and variables. Now the maximum gradients in the x and y direction are combined together for both the base and the input image. Then what the algorithm does, it creates images of the same size as the coarse image, as the original image. Then it finds the location of the control points, extracts the corresponding approximate coefficients, place the approximate coefficient into a black images, and the images are reconstructed to the original size. Now the reconstructed images provide the algorithm with a mask to tell where the control points are located. Here you have to note that I am using a 16 star 16 250 16 star 16 control point. Advantages: the ability. What are the advantages? This is where my process gets over in the wavelet transform. But what I have to now, what is the basic advantage of the wavelet transform? Advantages of the wavelet transform is its ability to compact most of the signal's energy into few transformation coefficient, which is called energy compaction. The ability to capture and represent effectively low frequency components such as image, background, as well as high frequency transients. The variable resolution theory, the variable resolution decomposition with almost uncorrelated coefficient. The ability of a progressive transmission, which facilitates the reception of an image at different qualities. Now if you see about the evaluations, like I said, approximately of using the Gaussian filter, we use PSNR. Here I am going to use something. Wavelet transform is far better than Fourier transform on the grounds of what? The quality of the work is done is much better. Temporal information is not lost in the transformation process. It tells us what notes to play and when those notes to play for a better output. Fourier transformation, wavelet transformation provides all the signal analysis as well as the signal nodes, whereas Fourier transformation does not provide that. It only provides the frequency transformation. In the wavelets, what do we have? We have here the application of the wave, that the MATLAB toolbox, wavelet toolbox. If you see in the MATLAB, it has various one-dimensional wavelet, two-dimensional, three-dimensional wavelet, specialized tools for wavelet. We also use denoising, we use wavelet coefficient selection, we use continuous wavelet, we use discrete wavelet, we use signal extension, we use image fusion. We can fuse both images using wavelet. That is the power of wavelet. Applications of a wavelet transform are object detection, face recognition, morphable models, face recognition, change detection, and edge detection. Where conclusion from this project is, I conclude from this project as being what I learnt is, so after all the presentation I hereby conclude that the wavelet transform is an effective way for feature extraction. It has various advantages as compared to conventional Fourier transform. It is unique in its understanding. A significant correlation present between the surface and the extracted energy coefficient. What I learned personally from this project: what is feature extraction, ideas and approach. What is feature extraction, ideas and approach. What is wavelet transform, how we used it in the what is the Fourier transform, how we implemented that, the various approaches, the advantages, the disadvantages, what are the advantages of the wavelet transform, and specifically the MATLAB use of various functions and the wavelet toolbox in the image fusion, in everything. I learned that personally, which is not used in this project, but still I completed the wavelet transform in the image fusion, signal extension, image extension using various signals. That's it. I have various I have the codes. The code is split up. I have split out the MATLAB code into 6 parts. The first part is the reading the image, the second part is the wavelet transform, the third part is the relative grading points, relative grading points. The fourth part is the fourth part is finding the maximum gradient in both x and y direction, and the fifth part is combining both the maximum gradient of x and y into the base image, and the construct the smaller images from the energy inputs into the desired feature. This is all. Thank you very much, Dr. Wu. I used a little bit commands on that, so thank you very much for that person. Thank you.